So in this first introductory lecture, which is about 45 minutes, we're going to look at why stochastic hydrology is of use anyhow, then a little bit about the course content, and then we end with some definitions from system theory that we will need in the remainder of this course. So I'm gonna pop up the pointer and move to the next. So stochastic hydrology actually derives from the Greek word, excuse me the pronunciation, stochastikos, which means being reflective, in reflective mood. And then that derives again from the verb stochastai, which is to imagine, to think deeply, to contemplate. But it also literally means to aim for the truth, like what a philosopher tries to do. And that comes from the word stochos, which just means target. So this is where it comes from. So this is why we see the archer here. And if we think about stochasticity, something being stochastic in real life, it means actually imprecision. You know, we're acting, we're not sure how to act, or we are not so sure about the true nature of something and what the true value is. So it's either imprecise knowledge or the results of imprecise acting. Interesting is to see these, well, this is sort of a thing that if I just kind of show this one, this is a nice game that we can play. That's the archer. Let's see if I can find it here. So that's a pretty game to play. So if we just, you know, if we just shoot an arrow like this, it always goes straight, right? But if we have some imprecision in the way we act, of course nobody's as precise as that, then actually the arrows won't go right away. So now if we sample where people are shooting, then basically what we get is something like a distribution function. So we don't know the real outcome, but we do know that it is maybe something between certain values, and it's more likely to be in the middle than on the sides. So this is an example of something that is stochastic, right? Well, you can play around a little bit with that yourself later on. Okay, so coming back to the lecture. So that is something that is stochastic in everyday life. Another thing that's stochastic in everyday life is that we're forecasting something to happen. For instance, this is the so-called Galton board, where you have marbles that are falling on packs, and they can actually go left or right of every pack. But it's impossible to predict which side it will end up on each pack. So for a single marble, it's very difficult to understand where it comes. But of course, if you release thousands of marbles, you will get sort of a predictable distribution. In this case, it's a Gaussian distribution. And that we can explore. So we know not exactly what will happen in the future, but we have a certain possibility range with a certain likelihood attached to it. So that's another example of stochasticity in real life. Now let's move to hydrology. So this is a map. This is what you can, if you go to, excuse me about the Dutch, but if you go to a site called Groundwater Tools on the Dutch Geological Survey, you can actually select a location and get groundwater series there. And then you can actually fit a time series model. In this case, a time series model that is driven by precipitation and evaporation. And what this shows is the percentage of variance of the data. Those are the dots explained by this time series model. And as you can see, it's not able to follow correctly 100% these data. There's always a residual between an observation and the model. And in this case, 70% of the data are explained by the model and 30% are not. And that's actually noise. And these residuals, you have to do something with it. You can ignore them, but you can also do something with it. Now, the question is, what causes the differences between a model and observations? If you think about not only a time series model, but think about a groundwater model, for instance, or a catchment model. Well, first of all, the observations themselves can, of course, be in error. You can think of the fact that, well, if you want to observe discharge, for instance, you have to measure a water height. There may be some wind on the water, so while you're measuring the water height, there is some fluctuation there. Then you have to turn that water height into a discharge. That rating curve may be in error. So in the end, you will end up with an uncertain value of the observed discharge by itself. If you think about your model, you can have errors in boundary conditions. So you have to prescribe, for instance, for a groundwater model, what the groundwater head is on the edges of the model or the groundwater flux. There's errors in the initial conditions. What's the initial groundwater yesterday to predict the groundwater levels today? So if you don't know exactly what the groundwater levels yesterday were yesterday, then obviously you carry over an error to the prediction of the current groundwater levels. And then finally, there's also the input, precipitation data, evaporation data. They can also be subject to uncertainty because they have been observed at a limited number of points. By itself, the observations of input can be uncertain as well. So all these things accrue to an uncertainty in the input. Then there's the so-called unknown heterogeneity of the parameters. For instance, a groundwater model, we probably will not know what the geological makeup and the hydraulic conductivity is in every location in the subsoil. We have to assume some form of homogeneity, and that makes for errors. There's also a scale discrepancy. Yeah? A model, like a groundwater model, for instance, may try to estimate groundwater levels average over larger blocks, maybe 100 by 100 meter, while you observe your groundwater levels at the point. So there's a scale difference between what the model predicts and what you measure. And there's finally model errors. Even the most physically of models always has some approximation of the true physics that are going on. For instance, we're using Darcy's law to describe the relationship between pressure difference and flux density. But Darcy's law itself is an approximation of flow that would actually obey the complete Navier-Stokes equations. We're neglecting certain terms of the Navier-Stokes equations to arrive at Darcy's law. And in most cases, this approximation is quite accurate. But if you have, for instance, preferential flow, you have Fisher flow, things like that, then actually Darcy's law doesn't apply anymore. Or if you have strong capillarity effects. If some of you followed the unsaturated zone hydrology course, and you saw that capillarity can be a major impact and actually leads to a different version of Darcy's law. And finally, and that is something that people sometimes tend to talk to, system may be chaotic, which means it's unpredictable, even though it's completely deterministic because of its dependency of initial conditions. We'll make a small sidestep to that after the following slide to see whether chaos is a thing to worry about in hydrological systems. So these are all causes why there's never a one-to-one match with your observations and your model outcome, even if you calibrate it as best as you can do. Now, this is just an overview again of all these different sources. Let's get me the laser pointer out. So you have a groundwater model that has that predicts the head at a certain time, 1, 2, 3 ahead, for instance, and it needs an initial groundwater head. It needs fluxes on the boundaries, or heads. So on the boundaries of the domain, you need to know what the groundwater head or the fluxes are. You need the input variables measured at a limited number of locations. So you have to interpolate it probably. There's errors in there, in the precipitation, the evaporation. You have some parameters that you don't know everywhere, like conductivity, storage coefficient, the surface elevation, the location and the depth of the drainage network, and so on. And all these together make up the fact that make that the model output is always in error. Now let's do a little time sidestep to chaos. Chaos is actually something, chaotic behavior is actually something that we didn't know until the 1960s. Before that, there was quite a physically reductionistic, physically deterministic view on reality in the sense that if we know, if we had precise information on the ice age and enough time and an electronic computer, we could pinpoint the weather at a certain date in a certain time in Tokyo. So uncertainty only existed in the subquantum world, below the Planck scale, and above it, it was thought to be fully deterministic. Then Edwin Lawrence found out that reality doesn't have to be so. He came up with a very simple model that described 3 atmospheric variables, but that was highly nonlinear, and that just a little error in the initial conditions made that the trajectory of the predictions became something totally different. This is called the butterfly effect. A flap of the wings of a butterfly in Tokyo will affect the weather in the Netherlands a few days later. Well, you can play around with this little game here, where you can see that if you change the initial conditions, the outcome is going to be quite different. So let's get out of here. See if this works. Go again to Kaon. So this little thing you can run. You can actually fool around with the parameters here. So here the system is actually quite deterministic. It is deterministic all times, but it seems very periodic. But if you play around with the parameters, it's going to basically get into chaos. And it's going to be very sensitive to the initial conditions. You can see a little small difference in initial conditions. You get a totally different trajectory. So because initial conditions are never fully known, even a fully deterministic system becomes unpredictable at certain forecasting lead times, and therefore you have to treat it as stochastic. Now, how is that when we think of hydrological systems? Well, it turns out that hydrological systems are actually almost never chaotic, because they are by nature dissipative. If we stop forcing the system, then it basically reverts to some equilibrium status. And that is often the case with hydrological systems. If we stop putting precipitation into a catchment, then eventually runoff and evaporation will cease, and that's it. There are some examples, however, if we think about, for instance, the connection between, if we think about human water connections, for instance, and for instance, and plant-water interactions, they can also be chaotic at times. Okay. I'm going to see if we can move this a little bit. It's not possible. Okay. So let's move on, and then go to. Okay, we established that we have these residuals, so there's a difference between what a model predicts and what the observations tell us. So how are we going to deal with these residuals? Well, in deterministic hydrology, we're going to do as if they are not existent. We're basically sticking our head in the ground and just move on and live with the errors. While in stochastic hydrology, we're actually going to face these residuals head on, and stochastic hydrology is really concerned with the residuals mostly. How can we predict them? Can we maybe exploit them to get better model predictions? What can we learn from them? And so on. That is what stochastic hydrology is all about. Now, before I give you some examples on how stochastic hydrology deals with these residuals. It's important to know that there are two ways of dealing with residuals. There are analysis where we have reality, which is this one here, or which is this. This is the real value that we're trying to get at, but we will never know because we are always in error. This is what our model says that reality should be, and this is the error or the residual. Yeah. Now there are analysis where we just deal with the deterministic model separately, and then we focus thereafter on the probability distribution of the error. So it's basically focusing on error, the error alone, and one of the techniques is called error propagation. That is what it does. The other way of doing that is not being not thinking about the deterministic model itself, but looking at the model outcome as a stochastic variable. So reality is a stochastic variable that we try to get the best possible estimate possible. So that's here, this head here means the optimal estimate with a certain uncertainty distribution of that particular variable. So the idea of a stochastic variable or random variable, that is actually what stochastic hydrology is about. So this is the way we're going to look at the outcome of our, or this is how we're going to look at the hydrologic reality as an outcome of a stochastic variable or random variable. Yeah. Now, what's the advantage of using stochastic models over deterministic models? Well, I can give you a number of them. First of all, the deterministic models are usually smoother than the reality. If the black line is the reality, and then typically a deterministic model will give a much smoother version of that. Now that smoothness is not a problem if you're dealing with average values, or you want to know what the mean water table is, or something like that. But if you're interested in extremes, so what's the likelihood that you have a very high or a very low water table, then obviously if it's too smooth, you're gonna underestimate the large values and overestimate the small values. So deterministic models are very bad at estimating the likelihood of extremes. And to mend that, stochastic theory enable you to generate equally likely realizations of the reality. For instance, one of these realizations is this dotted line. That is not exactly fitting the unknown real reality, which is the black line, but statistically it reproduces the right likelihood of all the values. So this is what stochastic methods can do. Second, it turns out that the best estimate from a stochastic model is not the outcome of the deterministic model. The best estimate meaning the one that has on average the smallest error. For instance, if I have a groundwater model and I have uncertain values of hydraulic conductivity, so the hydraulic conductivity has a certain mean and a certain spread around that mean, then if I put in the average or mean value into my groundwater model, that's the deterministic output, then the estimated heads are not optimal given the uncertainty in the hydraulic conductivity. And that is the reason is because the model is nonlinear. So for any nonlinear model, plugging in the deterministic value of the input or the parameters doesn't give you the output with the smallest error. And stochastic methods can teach you which input you have to use to get the optimal output. 3. Residuals also contain information. If we plot the residuals, between the groundwater levels observed and the output of the groundwater model, then we can see that sometimes they go all over the place. But for instance, especially in this part, you see that if the error is positive, so the observation is larger than the model, then there's quite a high likelihood that the observation or that the error in the next time step is positive as well. So there's a certain temporal persistence or correlation in the residuals. And we can exploit this temporal correlation in the residuals by a technique called time series modeling to predict, arrive at better forecasts, for instance. And that's another way of dealing with it. Another example is that if you account for uncertainty, you're likely to have much better decisions, to make better decisions or more rational decisions. I'm not sure if they're better, but at least they're more rational. For instance, suppose that we have a certain terrain and we are taking soil samples there. And these soil samples, we are measuring the lead content, and we have to decide whether to clean up that site or not. And we collected 100 samples and estimated the histogram, the frequency distributions of those samples. That's here, this one. And then this is the critical level. And you can see certain samples are above the critical level, certain samples are below. Now the question then is, given this outcome, do we have to clean up the site or not? Now, in a deterministic view, you would typically estimate the average of all the samples. And in this case, because it's lower than the intervention value, the critical value, we will clean up the whole site. But in a more probabilistic manner, what you would typically do is you would say, okay, what is the likelihood or probability that a given location on the site is larger than the critical value? And what is the cost? This can be health costs or liability costs. If it turns out that this, what are the costs attached to exceeding that critical value? Now, if we then take the probability times the cost, we get an expected cost of not cleaning up. And we can confront that with the cost of cleanup. So if the cost of cleanup are smaller than the expected cost of not cleaning up, you would leave it in the ground. But if the cost of you will clean it up, sorry. But if the cost of cleanup are much larger than the expected cost of not cleaning up, you would leave it in the ground. Obviously, this only pertains to mild pollutions that doesn't cause kids to get cancer or anything. So if something is life-threatening, this is difficult to do because it's difficult to estimate what the cost is of a human life, for instance. Monitoring design is another one. Suppose if you want to estimate the average groundwater salinity in this groundwater body, the green one. Well, you have a lake there, and there's also a building, and we are, as an engineer, as a consultancy firm, we have to pick the number of samples and the locations of the samples. And suppose we have 100,000 euros to do that. Of course, then we want to spend our money as well as possible. So we want to optimally place the number of locations that we can afford for the given budget to maximize the accuracy of the estimate. On the other hand, it may also be that, for instance, the municipality requires you to map out the salinity with a certain, or lead pollution with a certain accuracy. In this case, you want to minimize the costs given the required accuracy. Now, all these type of problems can be solved with stochastic methods. And then finally, this is the good old water balance. Suppose you have a catchment, and for this catchment or a polder area, we have the precipitation falling in. We measure the groundwater exfiltration for the Dutch-speaking people, which we call kwel. That's the groundwater seepage from deeper aquifers. The evaporation, the discharge to the drainage system, the change in surface water storage, the change in groundwater storage, and the change in soil moisture. So this is the water balance. And if you independently measure these, you will always see that you have a residual. So the water balance actually most of the time will not close. And this residual, even in a well-observed country as the Netherlands or Polder, will be close to 10% in most times of the total water balance. Now then the next question is, which of those terms do we want to measure better if we have a given budget to reduce this residual, to increase the accuracy of the water balance? Well, if we are able to, with stochastic methods, to estimate the individual accuracy of each of those terms, this is the variance, which is a measure of accuracy. The smaller it is, the higher the accuracy. Obviously, we will start measuring the term that has the largest value of the variance, because this is where our money spent will reduce the uncertainty about the residual the best, and the residual itself. So these are 6 examples of why stochastic hydrology is useful, and while worrying about model residuals is useful. Okay, we'll end this part before we break with some definitions from systems theory, because it's often handy to have that to understand some of the theory, especially when it comes to the optimal estimation and Kalman filtering later on. Now, if we try to model reality, a system approach tries to describe quite clearly what type of the reality is being modeled or described and which type is not. That's called the model or system boundary. Yeah. For instance, the system or model boundary could be the catchment divide, or it could be the aquifer boundary. It can also be a vertical boundary. For instance, we're considering only the soil until the bedrock and not the deeper groundwater, for instance. Yeah. Now then there's a so-called state variable. A state variable is a variable that once we know it, we can use it to predict the state variables in subsequent times, given that we know the input variables. Yeah. So, for instance, for groundwater system, this typically would be hydraulic head. Yeah. Input variables are variables that drive the system. For instance, for a groundwater system, this would be precipitation and evaporation, for instance. And output variables are related to state variables, though they can be derived from it. For instance, Darcy flux, once we know the head distribution, we can actually derive the output variable Darcy flux by applying Darcy's law on the head field. Yeah. So a state variable, like I said, is unique in the sense that if we know it everywhere, without error, we can, with only the information of the input variables, we can calculate what the state variable is going to be in subsequent time steps. This is called the so-called Markov property of a system. We only have to know the current state and not the states in the past to propagate the system to the next state of the next time steps. Then we have parameters. Parameters typically relate input variables to state variables or state variables to output variables. Parameter could, for instance, be the infiltration capacity of a catchment, the hydraulic conductivity of an aquifer, the porosity of an aquifer, things like that. And then there are constants. They are basically not changing in space and time, and are universal for the system that we look at. For instance, the gravity constant could be a constant. The density of water could be a constant. But what is constant in one system approach can be a variable in another. For instance, if we think about fresh groundwater flow only, then the density of water is constant, and it can be treated as such. But if we think about modeling the fresh saline distribution in coastal areas, then the density of water changes with space. So then it becomes a variable. Yeah? Now, just to give you a little bit of explanation of that, this is a catchment. This is the catchment boundary. It has a certain area A. There's rainfall falling on top of it. And we're looking, actually, part of that rainfall recharges the deeper groundwater, so that's lost from the system. And there is and all that water is stored on the surface and in the surface water system of the catchment, and the amount of water stored, the average amount of water stored in millimeters is V here, it's called V. And there is a certain output, discharge, in millimeters per time unit or meters per time unit. Now, if we make a system description of this, we have a state equation that propagates the state. As you can see, this is actually nothing more than the water balance. So the volume of water stored at a certain time is the same as the volume stored at the previous time step, plus the input from rainfall minus the part of the rainfall that recharges, that infiltrates and is lost to the deeper groundwater. The plus means that whenever P is larger than R, this is positive, and otherwise it's 0. You have to multiply that times the area of the catchment. So that's the input, and the output is the discharge. Now, if we parameterize the discharge as a linear reservoir, as is done often in catchment hydrology, we have that discharge is proportional, is a proportionality parameter times the volume stored. Yeah? Now, if we insert this guy here and rework a little bit so that we get T on the left side and all the other on the right, we arrive at what is called a system equation. You can see if we know the system at the previous time step and the input, we can get the system at the next time step. So this is our system variable. Q is actually an output variable. And once we know, this is is the state variable. Q is the output variable, because if we know the state, we also know the output. We have two parameters, R and K. R is the infiltration capacity of the soil, and K is the proportionality parameter. And then we also have a constant, A, that's the catchment area, that doesn't change. Yeah. So this is an example on how system theory can be applied to a rainfall runoff process.